Hello everyone. This session is about sharing a story about integrating Python into an existing Java application. My name is Tamas Rozman, and I work in the newly founded BlackRock office in Budapest within the AlphaGen technology team. And my background is a bit heterogeneous. I still consider myself primarily a Java developer, but I have experience with various other languages, including Scala, Python, KDB+, and Perl. And these come actually handy during this project, where the goal was to integrate Python to an existing Java application. Let me tell you a few words about this application first. BlackRock is a financial company and handles investments. And this application actually about making investment decisions. And in order to make investment decisions, it does lots of mathematical calculation with time series data. These time series data calculation can be simple averages and standard deviation with some secret sauce, and it goes as well to machine learning as well. So this is quite a heterogeneous environment, but the key is that it does mathematical calculations. And the task of the AlphaGen technology group, which I'm working in, is to make this calculation happen in production quality. Let me tell you a few words about BlackRock. BlackRock is the world's largest investment manager, and it has more than $6 trillion under management. These models that this application drives routinely make investment decisions for billions of dollars of client money, so you can imagine that they are very important. Okay, so about the application. You can imagine the application as a giant Spring container. So all it does at the beginning, at least for the superficial eye, is that it handles a complex calculation graph of Java objects, just like Spring. The differences are these trees are assembled at runtime. So there is a web front end where users can actually configure these calculations. I mean the hierarchy of these calculations. These are version controlled runtime, so anything that you make a change, it will be verifiable later. And this configuration is stored in DB, not unlike in Spring when it is stored in a Git or basically the project. It has a pluggable architecture, this system. So if you want to plug in a new calculation, all you have to do is to obey a few rules. One of the rules being just having one constructor for your object, and you have to annotate your classes in a special way. So we have several annotation types. You have to supply those in your class file, and basically you're done. You can plug in your jar file, and your calculation is ready to go. You can basically add to this tree of calculations if you want. About the data sizes, obviously this application would be nothing without actually executing the calculations that are stored in the configuration. Just a few numbers. One job can handle from megabytes to few hundred megabytes of data, so it can calculate on a magnitude of megabytes of data. We have a so-called alpha job, which is a root of several hundred jobs. This is responsible for one particular model, which drives the investment model for a particular fund, and we have hundreds of alpha jobs. So you can imagine it's quite a big hierarchy, and this system is quite complex in order to support these calculations, this complex tree of calculations. All right, and this framework, as I mentioned, it's very Java-ish, and it's a very successful framework in-house. So it was actually chosen from several competing frameworks to be the de facto standard for this type of calculations. And as I said, it's purely Java right now. Our goal is still to enable Python calculation into this framework. The question is, why? Why do we need Python calculation when we have this shiny new Java framework? The answer is that Python is very good at doing statistical analysis and doing machine learning tasks. And it is getting better and better. To be honest, it's much better. It has much better libraries to support this type of calculations than Java has. Python is extensively used by our data scientists who actually prepare those models to come up with the model ideas and actually make them happen and does the mathematical thing behind this calculation. So what the usual workflow is that they come up with some model and they come up with the model using Python code, some quick and dirty solution where they basically verify that the investment idea works. After that, they handle it to our department, who right now gets those initial dirty codes from Python and translates it to Java code. And this this conversion is sometimes tricky because Java just misses the necessary libraries. So we have to implement those libraries sometimes from the scratch, and it's quite time consuming. So our goal is to shorten time to production. So instead of translating the initial Python code with the Python libraries to pure Java, we can basically just get this initial code and translate it to a proper Python code, which is production quality, and we could plug in into this existing application. So basically, that's the goal. So we would like to make this calculation happen much quicker, and the reason is because these models are actually meaning money. So if a data scientist comes up with a model that says that this can earn as much money, so it is the return for this particular model, then if we just spend several months until it gets into production, it's very, very easy to see that, oh my God, we lost that amount of money for the clients because we were not in time. So this is the base idea of integrating Python into this framework. Okay, so we accepted we need Python. The next thing is that practically all of the Java developers know now Spark, and Spark can do both Java and Python, and it can also do Scala. So why we just not use Spark for this purpose? And the answer is we already have an existing execution framework, as I mentioned, and it is based on hierarchical tree of calculations. Spark is not really about hierarchy, it's about handling vast amount of similarly structured data. Also, our data is not really big data, as Spark is basically for big data. We have maximum several hundred megabytes per job. So it's not, our thing is not really big data, so Spark is not the ideal candidate for this. And the last thing is that Spark actually cannot really mix Python and Java code in one job. So our application actually contains a hierarchy of jobs, and our goal is to enable plugging in just a piece of Python code which does some particular part of the calculation. For Spark, if you do something, it should be purely in Python or in Java. You cannot really mix within a job. So that's the reason. So I think we all understood that we need Python. The question is how to start. And actually, after talking with the Python developers and Java developers within the firm, actually there seems to be a few challenges because the mindset of the Java developers and the Python developers are a little bit different. Let me see the differences. First, I start with a legal notice. So any characters or stereotypes appearing on the following page are fictitious. Any resemblance to real persons, dead or alive, is purely coincidental. So this is required, so I don't want no feelings hurt. All right, let's see the comparison. Java developers. Java developers love abstraction, so abstraction of abstraction, and maybe we forgot what was the original idea, but abstraction is the king. And for my experience with this application, is that the time series data is quite complex and hidden in generics and classes, and it's beautiful, but it is very hard to follow. I actually spent several hours to understand the basic structure of the Java in this application, how a time series data is built of. For Python developers, it's just do it. They don't really care about abstraction. They want just get the job done. They need something. For example, instead of this complex hierarchy of time series data, they just have a de facto standard of a pandas, so-called pandas data frame, which is essentially a table in the memory. All right. For Java developers, we demand clear interfaces and clear types. This is a paramount for all Java developers. Actually, the second question I got with this application from Python developers that, oh, all these types, they just don't want it. Can we just use object instead everywhere? And this is because they believe in the so-called duck typing, which is practically the opposite of what Java developers do. And like, all right, for Python developers, code is the minimum number of characters. As I mentioned, the previous one was the second question. Every time if I go within the firm to Python developers about evangelizing this system, the first question is always, oh man, please do not add a single line of code to my existing code. I just don't want that. I just want the minimal number of characters that I can live with. Why for us Java developers, we know that IDE will take care of the code. So if we just need an extra line, then we just don't care. All right. I feel that sometimes Java developers are a little bit over paranoid, so we care about hash code, equals, thread safety, and all these type of things. Where for Python developers, they just relax. They don't care about things. Relax, you. That's their attitude. Altogether, I would say that the Python developers see Java as a quite bureaucratic language with a lot of things that is not doing the functional thing that they require. By Python developers, but Java developers think of Python developers as they are wide west. They can do a lot of things and they don't care about the beautiness of coding. So this is our initial setup. So this is where we started the project from. So let's see what we can do with it. So our goal is enabling Python calculation in this existing application framework. Let's come up with a plan. And the plan is, first, we want to make something work. Let's call it mission backbone. It won't be pretty, it won't be very useful, but it still gets the job done. The second mission is mission muscle. We want to make it usable. It will be not the prettiest, but it will be usable by an average user. And as the third phase, we want to make it look good. So we want to make everybody happy at the end. And these phases will build upon each other. All right, so let's start with mission backbone then. The mission statement is, we want to have some kind of request response between Java and Python. Java sends a request, Python sends a response. We want to be effective, so we want to have enabled binary transmission between Java and Python. We need to handle exceptions and we need to handle logging. So this is our goal for this mission. All right, let's start with some technical notes. You would think, and I did when I started this project, that Python is very strong in threading, because you keep hearing that Python is very good at data crunching, it is very good at machine learning, so you would imagine that it requires a lot of processing power, and a lot of processing power means handling threads properly. And actually, yes, Python has a threading library which enables you can use it on your own. However, Python has different implementations, and the reference implementation, which is called CPython, is special. This has a so-called global interpreter lock, which effectively means that the Python interpreter will be single-threaded. So you cannot really use your Python as a multi-threaded server. You can only use it. Python code can only run in one thread. Why? Why is that we are thinking Python as a machine learning language? The reason for that is that Python has a lot of libraries, and those libraries are not written in Python, but are written in C or C++. So whenever you start a matrix multiplication, you can do it in multiple threads, because that part of the code is written in C, and C will take care of the threading itself. So that's the reason why, that's the misunderstanding, that why you would think that Python is very strong in threading, why in reality it's not. I have to add that this global interpreter lock is present only in CPython, as far as I know. So there are other versions we could use. For example, there is another version which is called JEEConf, which is actually lives in the JVM. So it could be very handy for us if we want to integrate Java to Python. The problem with that is that they are lagging behind in versions. So the reference implementation CPython is right now around 3.6. while JEEConf and many of the other things are at 2.67, and it's quite different beasts. And I can't really go to the data scientists who actually use CPython and 3.6 that, oh man, we have this new shiny Java framework and we want to add Python to it. And in order to do that, we need you to degrade your current code and libraries from 3.6 to 2.7. This is not the kind of conversation you would start at the beginning. So basically, we left with the choice of CPython and with the global interpreter lock, which essentially means that we cannot have a multi-threaded Python server. We need to have a separate Python process for each of our threads in Java. All right, some words about data sharing. We agreed that we will have separate processes for Java and Python. We need somehow share data between Java and Python. How to do that? Our initial thought was to use some kind of open source framework. There are a few of them. Most notable of them is the so-called Py4G, and Py4G is the one which is used by Spark. So it was an obvious candidate. And we actually did a pilot which used Py4G, but we found that it's kind of difficult to use. Obviously, it's production quality because Spark is production quality and it works marvelously. But if you just get the pure Py4G, it's just a little bit hard to use. We get often exceptions like proxy exception X, and you don't know what happened. And it does a little bit more than us. So it handles threading and it actually uses sockets to communicate. And it is not very well in our environment. We have big machines where handling these sockets is a little bit difficult. So it's at an additional layer. So we decided to come up with our own implementation. own implementation. The obvious candidate would be file-based communication, so the request would be written by one of the processes, and the other process would read that result from the file, from that same file, and we could exchange data like this. But for some reason, it doesn't sound very efficient. It requires disk sync, and yeah, it's a little bit old-fashioned. We still use at some points, not in this project, but yeah, it's not the nicest solution. So what we started to work is actually the so-called memory map files, which I heard about that before this project, but considered to be something pretty low level and pretty hard to implement. But actually, it proved to be pretty easy. So memory map files or shared memory is essentially a file on the file system. So you get a file, prepare a file, and after that, what you can do, you can open a window on that file at any point, and say that I need a buffer from this pointer of the file. And from that point, your buffer will be a direct buffer to that particular virtual memory point. So you can write anything into that buffer, and it will be immediately visible by other processes that can basically open the same file. So basically, you will have a direct buffer access to a special virtual memory segment, which is visible by any number of processes. And if you write into this buffer, there is no interim buffer need, so this is a proper memory buffer, and there is no disk sync required. So anything you write into this buffer, without disk sync, it's immediately visible by the other process. So we decided to try this, because it seemed to be that it's quite well supported both in Python and Java. So we thought that it can speed up our process, because we can, without using any disk thing, we can basically speed up the data interchange. I have to note that serialization still matters in this case. So if you use a traditional serialization method which uses your heap in Java or Python, then you still will have a big data structures in the heap, and they will be copied into this buffer. But there are methods, it's quite popular recently, which is called zero copy serialization methods, which use this memory buffer directly for the serialization. So essentially, you can use this memory buffer at its full speed. All right, so we decided that we will have separate processes and we will use memory map files. Let's come up with an initial interface. And this initial interface would look like, first we would start a request handler, which would mean that we are starting somehow a Python process. This Python process would actually add the request handler, similar to an event handler in Java and other languages. So it would say that under the name calcMySignal, if I get this request, I will call this function, which is called calcMySignal. So this would be the start. You would start a Python interpreter. It would register a request handler. If you want to do something like calculation, you would actually need to request a request buffer for this request handler. This would return this memory map file portion as a buffer, and you could write a request into it. Obviously, in this case, we are in the mission backbone, so it will be up to the caller to find out the proper binary format. It should be obviously the same as required by the Python side, but we will handle this in the second phase. So you have to know how to do the binary serialization here. You will send a request. You send that I want to do the calculateMySignal. You can add the text parameter if you want, and that's it. After that, the framework will call you on the Python side. This is Python. It will call the function, which will have several parameters, namely the request name, request parameter, and the most important ones are the input buffer and the output buffer. So what it would do is read the binary request from the input buffer, which is a memory map portion. It will deserialize it, process it, and write the results to the output buffer, which is again a memory map portion, a direct buffer. And once it's done, Java can basically check the response, whether it was successful, and if it was successful, it can use this memory map buffer again and deserialize the message, the response. Yeah, that's our goal. Let's see how we can do it. What we do is actually we are starting Java. From Java, we are starting Python as a sub-process. We do it by using process builder, and we make it work in a way that Python standard input and standard output are attached to Java input stream and output streams. And we communicate each other by basically writing, if we want to do Python something, then we write a comment to Python standard input, standard output, and we say let's say a comment, we write a comment, and Python would parse this comment, and would write the response into its standard output, which is an input stream in Java. So basically, you would have this request response using standard input and standard output. It would mean that basically at the time only either a Java thread or the Python process is active. So they are not active at the same time. If the Python is working, Java is waiting for the response of Python, and vice versa. If Python is not working, then it's up to Java, and Python is working for a command from Java on its standard input. Okay, let's see a simple conversation. So let's say I have a request handler which is add numbers, and it requires 2 numbers. This is what I would write on the standard input of Python. Python would parse it. It would check whether it has an add number request handler. Let's say it has, and it would basically add the numbers together. So it would say that success, I would, and that's 333 plus 444 is 777. So this is a very simple example. What if we have a complex calculation, which is actually true in our case, where Python doesn't know all part of the calculation, but have to call back to Java? Let's see. I want to have a request handler which calculates value of expressions. And let's call it calc expression. And in a string, I would pass the expression. In this case, we would have a part of the expression, I called it my Java func for clarity, which would be calculated only by the Java. So Python doesn't know how to calculate it. What would happen in this case that Python would do its part, so it would calculate the square root of 36, and which is 6, and I would ask Java to calculate this my Java func for this result, which would be it would write to the command line of Java to my Java func 6. Java would say that okay, this my Java func is actually a power function, 2 to the power of the parameter, so 2 on the power of 6 is 64. So it would write that okay, I calculated it for you, success. And based on this information, Python conclude and can say that all right, the full result for the calculation is 65. So this is kind of a more complex example. Obviously, these commands are not written in plain text into the standard input and standard output, because there are some naughty Python algorithm that writes something onto the standard output, and it is not command, and we could still identify it as a command. So our thing is that we add some hashes to it and some magic patterns to make sure that what we interpret as a command is really meant to be a command. All right, so far I haven't mentioned anything about memory map files, which I promised. So far it was just a communication using standard input and standard output. But obviously this previous example will be dead if we want to pass megabytes of data. It's just good for one line of data. We could add this memory map file thing using the same thing, using this standard input, standard output method. The thing is that we would open one file for writing Java and one file for writing Java, and it would be read by the Python process, and another one which would be written by Python and would read by the Java process. We make it to make sure that there are no write conflicts, which is actually, it's an extra measure because I already mentioned that at the time only Java or Python is active, but just we wanted to make it sure that it's operatable. It may be removed in the future versions, but right now we want to make sure that Java only writes one particular file and Python writes only one particular file. And what would happen at the beginning is that we need to basically negotiate the name of the files, what we read. So if we use this memory map feature, then the initial, when we start up the Python as a subprocess, one of the first commands we use is that we tell Python that it should use this particular file, temporary file, for writing its responses to Java, and Java will send its requests into this temporary file. So basically, after this conversation, both Python and Java knows which are the memory map files where it can locate the requests and responses. And after that, let's say that we can start the discussion. We would like to add the same thing that we did before. We want to add numbers. But now we want to add a bunch of numbers, not just 2 numbers, but thousands of numbers. So we can have a new request handler, which is called add vectors. But now we wouldn't write the numbers into the standard input, before we actually firing up the command, we would write all the numbers in binary format into the memory map file. After writing this information, we would call Python. We would write these add vectors and the length of this binary file to the standard input of Python, so it could know that, okay, I need to read all these numbers from this memory map and need to add them together. So what it would done, it would first look into the temporary file, the memory map file, read the binary format, the numbers, it would add them together, and after that, it would write the result into the other memory map file and would return writing success into its standard input, and also the length of the binary serialized method. To be honest, we use these numbers. I mean, the length of binary for convenience, we can do without it. So if we have just the file, it works as well. But we make it easier our life, because we already know when we go into the file, we don't have to, the serialization method doesn't have to know how long it will be, because we already passed it using the standard input, standard output. All right. This is good, but what if we have some kind of an error during the processing? It's easy. Instead of returning success, we return error, and we write the error message into the memory map file again. So it's pretty much similar, which means that that we can have a proper Java expression containing the data from the Python expression. Luckily, Python have a similar exception handling mechanism to Java, so all of the exception can have a name. They have list of parameters, we convert them to strings, and it has a message. So an example case can be that the name is, for example, unbound local error. This means that one of the variables is not really defined. It says which is the parameter contains the actual location, so the local variable is referenced, and we have the full message, full stack trace for Python. So this means that it's quite handy, because from the Java side, if we get any error, we see it in a proper exception message. All right, we have now request response. We have binary transformation. We have exception handling. All we left is logging. It would be quite handy for us if our Python logs would appear in the proper Java log. So we just don't want to have another log for our Python calculations, because it just makes life much harder and support much harder. So nothing prevents from us to actually doing the logging in the Java log, because we have, as we remember, we have the Python, either the Java thread or the Python process active at a time. So our logs will contain the things in time. So they will be not unsorted. It will be a proper sorted log, which either contains a Java log message or a Python log message. And we can actually do that. You remember that we have standard input and the standard output of Python. We process the standard output of Python because we are looking for commands from the Python side with this hashed and magic pattern commands. But it can happen that whatever we see in the standard output is not a pattern and not a command. In that case, we can decide. We can basically just get that input and put right into our standard output of Java. This was our original plan with this framework, but it's just not very nice. So you would see the Python logs, but there wouldn't be real logs. So and they couldn't be redirected, and it's basically just a standard output. So what we decided is to basically format the Python log in a special way. Just add some magic pattern to it and a well-defined format, so that we can identify on the Java side if we get something which is not a command, not a hashed command. We can decide if this is just some random message or a log message from Python. And if it's a log message, we can actually incorporate it in our Python Java log. This is an example. So you see in blue the normal Java log, and the yellow ones are actually from Python. And it's pretty much similar to the Java one. We added two things. One is that obviously the Java log will contain the Java location. So we need to parse the Python log and add the Python format, the Python location as well for reference. And the other thing is that standard output is buffered. So it can happen that you're writing logs on the Python side, but you are in a long-running calculation. And it can happen that Java will pick up that log message several seconds later. So that's why we also include the Python timestamp for reference. All right, and this is done. Mission backbone done. We made it work. Obviously, it's not very usable at this point because we expect the caller to fill in binary format, which is not very handy. So let's move on and let's start mission muscle. All right, what we want to achieve is a proper format with, on the Python side, we want to have classes and methods instead of this request handler thing. And we want to handle serialization as well out of the box. All right, this is our destination. So we would like to have, this is a Python class. This is the init is the constructor in Python. So we would like to have proper constructors and proper methods in Python instead of this request handler. From the Java side, we would implement this as we would call it a Python stub. We would pass the file name, a Python file name, the Python class name in string, and also in untyped parameters, the constructor parameters. And we would call with a special method which is called Python call, and the method name would be clear text, and the parameters would go as an untyped list. So this is our goal for this mission. So how we do that? To be fair, at the beginning, which looks like the Python class is really a stateless service. So in our case, and this is one of the reasons why we didn't go with Py4G, we just want to be stateless all the time. So having a constructor and a method is really just a convenience. Really, under the hood, we are just doing a method call where actually the constructor parameters and the method parameters are both passed. And for the safeness, we just prepare first a class, and after that, we prepare a method. But after that, the method the whole class will be garbage collected. And this is basically a design decision. Our architecture works like this, and this is much easier to implement. So Python is just a stateless container. It lives, the request lives until the response is returned, and nothing happens on the Python side after that. All the objects are garbage collected. How we would implement it? We would build on the previous request handler method. We call it platform call request, and we would add all the class name, the constructor parameters, and the method parameters to the memory map file. We would call platform call request, and we would, on the Python side, we would basically deserialize the class name, the constructor parameters, method parameters, would call the method, instantiate the class, call the method, and return the result in the memory map file. So this is pretty easy. The real meat is in the serialization. And we opted for a simple and flexible for small data. I will talk about it a little bit later. This is JSON. And we use binary zero copy serialization methods for our big meats, which are the time series data. How we do that? It's basically a simple JSON. It looks like a simple JSON serializations when we start to serialize an object as a JSON. And we have hooks where if we find something which looks like time series data, which is a time series data, then we basically serialize it into the memory map buffer immediately. While the JSON is kept on the heap of the JVM or the Python. So basically it's like a JSON but with an addition that some of the types are actually immediately serialized to the memory map buffer. And in this case, JSON will only contain the offset where we can start, where the serialized binary format is found in the buffer. And that's what I showed in yellow at fair. So that actually is an example for our system. So it says that we are serialized in JSON at signal time series. It has an ID, it has a data type, and the time series data there is serialized in a special binary format, and it starts at the offset of whatever I showed there. I have to add that there is no magic bullet for serialization, so we need to do explicit serializers for all types. So there is just no way of converting arbitrary Java types to arbitrary Python types automatically. We need to have explicit serializer for all these type of things. And the reason for that is we want Python to be Python, so it's just it doesn't make sense to force Python to use the Java structures. It just takes the fun out of it. And to be fair, Python has its own data structures for mathematical calculations, so we should convert them anyway. And we cannot do it automatically. We need explicit serializers for that. All right, let's see the typical sizes. The previous example, as I mentioned, the small data is serialized in the JSON, but you can see that actually the JSON at the end will be around 500 bytes, and the time series data, the binary, will be 1 megabyte to 200, 300 megabytes. So you can see that opting for JSON as a small data doesn't really add any overhead, so we doesn't really care. We just care about that the bulk of our data is put in Python. And that actually means that regarding objects, most of our objects are, the number of objects we serialize in, most of them are in JSON, so we can keep it simple, but only the heavy objects are done in Python. So I would say that 80% of the number of objects are serialized in JSON, and 20% are serialized in binary, but still you can see the data volume is quite different. All right, we finished mission muscles. So to make it workable and make it usable actually, all is left to make it look nice. And welcome to mission skin. And we are divers, so welcome to mission skin. And all right, let's see the mission statement. So for the previous example, Python looked quite right, so it was a proper class and method. But on the Java side, it was a little bit ugly. We were preparing methods with clear text names of classes. When we call the method, we needed to supply the method name as string, and we pass the parameter as untyped list. This is not something that the Java developers likes to do, and yeah, it's a bit of ugly. We would like to remedy that. And the other thing we need to add is the so-called plugin. So obviously Java is a compiled language, so if you want to do anything, then you need to compile it. But for Python, in theory, it is very easy to add the new Python code and without actually doing all these release processes. And one of the key goals we had in mind with this plugin signals, that we would like to enable a data scientist or anybody to plug in Python code into this system. Obviously not the production system, we have regression systems, but we wanted to make it possible to run Python code basically as simple as it's possible. So basically you just supply the Python code and it would be able to, the calculations would be able to use it. And for that, we needed to make sure that we can plug in signals as easy as possible. So this is our mission statement for mission skin. So the changes. You remember that we had this Python class and methods previously. What we added right now is first some annotation-like things in Python, which does add some auxiliary information, just like description. We add some information also about caching and some actual information, but we need these to make it actually usable on the web front end. And what we also added is the type parameters in Python. It's a bit ironic because Python doesn't really care about types, but still you can supply types as a method parameter from 3 point something, so in the newer versions. I say ironic because you can supply them, but Python will not make sure that they are enforced. So you can say that window is int, but Python will heavily accept string, and nobody will notice until you face an error. So it's more at this point in Python. It's more like just for the description. But it comes handy for us because we, as a Java, we want to generate Java stubs based on that, so we need this information. So in this phase, we need these annotations and the Python part, and we need the Python developers to supply the type parameters as well, so that we know on the Java side what type of information we need to supply, what type of data we need to supply. And if we do this, our goal is to the Python class looks like a Java class. So you would have a proper constructor with proper type parameters, and you would have the exactly same method. So you could call it by calc execute instead of supplying the method name with parentheses and with a string, and you have type parameters instead of untyped lists. All right, in order to do that, we will need something like Java annotations but in Python. Get the annotation data from Python to Java, compile Java stubs so we can plug into our existing infrastructure, and everything should be put in a jar because this is what we need in the structure, in our infrastructure. I will not go into details how we get the annotation data from Python to Java. I hope everybody is clear that we can do that. All right. Python has no annotations, but have something like annotations, look like annotations, and these are called decorators. It looks like the same. But they are not like them. So decorators are actually higher order functions that dynamically alters the functionality of a method or class. This is the thing. But we don't really want to alter anything. Yet we can still force Python decorators to work like Java annotations. We just basically don't alter anything. We return the function or the class as it is, and we attach some metadata to it regarding these descriptions and stuff which we need. All right, so we have the annotation metadata, how to compile it. And this was actually surprisingly easy for us. We first wanted to have some quick and dirty solution just to make it work because our application expects annotations. And we wanted to make it work with some quick and dirty Java compilation thing. But it proved to be so easy and so manageable, so we stick to it. It's basically as simple as generating the Java stuff, the pure Java code into a temporary folder. You don't have to care about the hierarchy, just like the package structure that is usually with Java. And that's it. You add it to the Java compiler. You set the class path. If you set the class path of the application, everything will be inherited, so you don't have to care about Maven and all that stuff. It's automatically whatever you have in the class path, whatever you have in your application, it's accessible to the compiler. And that's it. You compile. I don't go into details because it's purely from the Java documentation. And you can create a jar the same way from one flat structure. You just have to supply the package path as a parameter when you're preparing the jar. So it means that it's pretty easy without just a temporary folder to prepare Java compilation. All right, that's it. We finished mission skin. We finished enabling Python calculation into Java. Let's have a summary. So we had a Java integration which integrated Python and Java on the same host. Data interchange was doing with memory map files. We used hybrid serialization, JSON plus binary. And we generated stubs runtime for the seamless Java experience. So takeaways. Obviously, Python loves Java from now on. Yeah, it's not true. It was not our intention. But let's see some real takeaways. Overhead. This is a common question, and we did tests for that because that was the primary concern about this solution. But I would say that depends on the use case. If you have calculations which run for milliseconds, then obviously it doesn't make sense because it will be some at additional layer. But we found that actually with calculations which span usually seconds or stuff like that, the overhead is invisible. And the overhead is actually not because of the memory copy to this memory map buffer, but more to the serialization and the deserialization. So it really boils down to the serialization method that you use. But we found that if it's not milliseconds, the calculations that you use for, so yeah, you are using it for a big chunk of data, it's basically invisible. And to be fair, Python is sometimes quicker with mathematical algorithms than you would write it in Java. So sometimes it can be even quicker, even doing the overhead with the serialization. We can do a seamless Java experience, so we can basically call Python just like a Java class, and essentially our application doesn't even know. I mean, this framework that I talked about, it doesn't even know that there's Python on the side. It just knows that there is a jar. It contains proper Java classes, and that's it. All right. Another lesson learned. Shared memory for data exchange is pretty easy. It's much more easier. I recommend everybody, if you're not familiar with it, take a look. It's pretty easy to use, and it's very efficient if it's needed. Compiling Java from Java, I would say this is also a surprise. It's very easy to add the compilation from Java, and I would say it was pretty amazing to see because I constantly have problems with Maven and all these things to work together. And if you have this Java-based compiler and you have the application, it's pretty easy to do something like that. And a few words about Java and Python for calculations. Actually, it proved that it makes sense to go for Python in some cases, in case of mathematical calculations. One of the first things we did port some of the code from Java to Python to make sure to see the comparison, and it seems that it's much more dense. So we have these libraries in Python, and the initial thing, I think we ported some code which was, I think, 80 lines in Java, and in Python it boils down to 10. Or 15 something. So the ratio is probably 5 times. So you can write the same thing in Python 5 times less code. And Python is most of the time you don't even need loops because there are some declarative ways of doing mathematical calculations there. So I would say that it actually makes sense. It actually made sense to go for Python in our case because we did calculations in a way that can be better done in Python. Obviously, Java is much better for actually building the framework and making it happen because Python is not very good for, I would say, it can be done, but it's much harder to write production quality, big amount of production quality code. But if you are doing calculations which are quite constrained, so they have input data and output data, it just makes sense to do them in Python. And that's it. I added some further readings, so I don't go over them right now. You will see it in the somewhere in the website after this conference. And thank you very much for your attention. I'm afraid we ran out of questions. Okay. I think there will be some discussion forum open on the website after. So if you have questions, you can try to put them there, and I will try to answer them. Thank you very much.